Hey everybody, we are combining the topics from the last couple of videos to come up with our final big idea, the most important idea at least, when it comes to energy, and that's known as conservation of energy. And so by the end of this video, you'll have an idea of what conservation of energy means, where it comes from, and then how we can apply it to problems. And then we'll get practice in class doing problems for the next couple of days. All right, so first thing, all I want to do is consider the work that might be acting on an object. That's what I'm starting with. Let's look at all the work that can be done on an object. Okay, I want to look at the total amount of work done. So by definition, I'm looking at the net work. Well, when I look at the net work, I add up the work done by all the different types of forces, right? If there were 20 forces, I would have 20 things written down. If it was just one force, just one thing. But remember, we broke our types of forces into two categories. We had conservative forces and we had non-conservative. All forces fit into one of those two categories. So if I'm looking at all the work done on an object, that would mean that I'm including all the work that's being done by conservative forces combined with all the work that's being done with non-conservative forces. Now, again, there might be a whole bunch. There might be like 20 conservative forces if it was a really challenging problem. And there might be like 3 or 4 or 5 non-conservative forces, but they're going to fit into one of these two categories. Okay? Well, let's take it a step further. We saw from the last video that one type of non-conservative forces is friction. Let's, like we often do, ignore friction. In fact, let's ignore all types of non-conservative forces. Let's just say that for a certain case there aren't any. So any type of non-conservative forces, we are eliminating them. Therefore, what I have is that the net work done is equal to the work done by all the conservative forces. Well, we saw last video that the force of gravity is a type. And to be honest, that's really the only type we're going to be paying attention to for at least the next couple days. There's really only one other example. But for right now, let's only look at gravity. So the work done by gravity. All right, let's say that's the only conservative force that's acting on it. And that makes sense because pretty much all the problems we've been dealing with include gravity in one way or another. So I have that the net work is equal to the work done by gravity. Well, that's equal to m times g times h naught, oh my goodness. That's equal to h naught minus h. All right, well, if I have the net work equals mgh naught minus h, that's mgh naught minus mgh. Remember though, we had this thing called the work energy theorem. And the work energy theorem says W net is equal to the change in kinetic energy. So for here, I'm going to put 1/2 mv squared minus 1/2 mv naught squared. That's equal to, well, this thing, mgh naught minus mgh. Okay. Well, I have some terms that have the little naught, the little initial before symbol, and I have ones that don't. Let's get all the initial things on one side, like I'll swing this one over here, and the ones that have like final onto the other side, which will leave me with the following. This stays, so I have 1/2 mv squared. I swung this one over, plus mgh equals, this one will stay, mgh naught, plus I swung this thing over here, 1/2 mv naught squared. Haha. Well, if you look at this equation, this is very interesting. Another example of an interesting thing popping out. Okay. Remember, this term here was kinetic energy. This term here was gravitational potential. Both of these are like the final form, right? The initial forms are on the right side. This is kinetic energy after some point. This is the gravitational potential energy after some point. So on the left, I have all the energies after. And over here, this is initial gravitational potential energy. This is initial kinetic energy. This is initial energy here. And what do we have at this spot? An equal sign. Oh man. The energy something has in the beginning is equal to the amount of energy it has at the end. Or the total energy of an object is staying the same. Now remember, we had a big starting point, assuming this. Ooh, I don't know why that's all getting erased. Assuming that there are no non-conservative forces. I want to write this down. This is a huge idea. Let me get my green pen back. Okay, so the total energy, that's not green. The total energy of an object remains constant. As long as there are no non-conservative forces on it. As long as there are no non-conservative forces acting on it. Bam. Well, another way we can say that the force is remaining constant is if we say that energy is conserved. I can put in some exclamation points, that seems important. So as long as we're saying like there's no friction, there's no pushing forces, all types of non-conservative, the energy, the total energy, if you add it up, stays the same. So let's look at an example. I have a block, this orange block here, that's sitting on an incline. There's no friction. It's starting at rest. I'm holding it in place. Then I'm going to let it go, and it's going to start sliding over down the ramp. Okay, it's going to start sliding down this way. And I want to find the velocity or find the speed of the object when it gets to the bottom. Okay, this would be a classic inclined plane problem before, or maybe like a kinematics problem if you were just focusing on like down the ramp, if we knew like the length of the hypotenuse. But we can now apply the idea of energy. And if there are no non-conservative forces, for example, no friction, then the energy is conserved. So the box is starting at a vertical height of h. And then when it gets down to the bottom, since I'm measuring h from the bottom, the height here is 0. Well, let's try and apply the conservation of energy. Whatever the energy is here in the beginning has to be equal to the energy it has here. Well, we know of two types of energy. There's maybe the kinetic energy and there's the gravitational potential. If it's conserved, that total amount, if I add it up, has to stay the same. All right, that's what energy conservation means. If I add up all the energies before, it should equal all the energies after. Well, in the beginning, it says that the object's not moving. So if V naught's 0, that whole term is gone. So I have mg h naught. At the end, well, now it doesn't have any height. It's at the ground level. It's at h equals 0. So this is gone. So I have that mgh naught equals 1/2 mv squared. If I solve that equation, notice my masses are going to cancel. I can get this 2 on the other side. that equals v squared, or v equals 2gh naught, all under a square root. Look how easy that was. I didn't have to break anything down into components. No trigonometry was needed. I did not in any way have to know this angle theta. If I'm assuming, and if there's no friction, so no non-conservative forces, I can just add up the energy in the beginning, set that equal to the energy at the end. No components. Remember, all these things are scalars. There's no components anyway. There's no vectors that you need to. We can use this method to, for the most part, in a much easier way now, solve for things like speed and height and different types of energy much easier than we've been doing in the past. So this is the idea of conservation of momentum. It really just came from us looking at the work that might be happening on an object and assuming that there's no non-conservative forces. It's saying that if you add up all the energies an object has in the beginning, if you just go through a checklist, does it have kinetic? Does it have gravitational potential? Then you can set that energy equal to what it has at the end. Again, go through a checklist. Does it have kinetic? Does it have gravitational potential? Add them all up. They have to be equal to one another. All right, thanks for watching.